Thank you very much, Arnaud and Christophe and Paul. And so this is about unbiased MCMC with couplings, and this is joint work with John, who is here, and is going to present half of the talk, and Yves Atchadé, who couldn't make it, but did very significant contribution to this article as well. So the presentation follows very closely the structure of the article, and hopefully the content of the article as well. It starts with some background motivation about MCMC, the bias, and parallel computation. So the setting is that of a continuous or discrete space of dimension d, on which there is a probability distribution pi that we're interested in. And the goal is going to be to approximate the distribution pi, that is to approximate expectations of test functions h with respect to pi. H could be, for instance, indicators or polynomials. And we're going to come up with unbiased estimators, that is random variables with expectation equal to those expectations with respect to pi. And so Markov chain Monte Carlo methods are commonly used to approximate challenging probability distributions. They work as follows. You start by sampling x0 from a distribution pi0, which is typically not pi, and then you iteratively generate xt given xt minus 1 from a Markov kernel p. You do that for a certain number of steps, capital T, and then you can come up with an ergodic average over the chain, perhaps after discarding the first b steps as burn-in. And for any fixed choice of t and b, this estimator is biased. Right? The usual justification for those estimators come from letting t go to infinity. But for any fixed b and t, the estimator is biased. And so it will not be consistent to just sample independent copies of this estimator and hope the average of those independent copies to converge to the quantities of interest. So let's take an example of an MCMC algorithm, the Metropolis-Hastings algorithm. So this is what specifies the kernel P in that case. So from a state xt, a proposal x star is drawn from a Markov kernel k, and then accepted or not as the next step of the Markov chain, according to this Metropolis-Hastings acceptance ratio. And so xt plus 1 is either equal to x star or equal to xt. So this plot shows the marginal distribution of the Markov chain in the case of Metropolis-Hastings, with the target being a univariate normal centered at 0 and with variance 1, when initialized from a distribution that is centered at 10 and with variance 9. So over 200 steps, the marginal distribution of the chain goes towards the target. And from looking at this, we could say that after 100 steps, the marginal distribution of the chain looks indistinguishable from the target distribution. So from this, we could simply discard the first 100 steps and consider the average over the following 100 steps to be nearly unbiased for the quantities of interest. Difficulty is that in many scenarios where MCMC is used, the distribution is perhaps high-dimensional or defined on a space that is complicated to visualize, and so we don't know exactly, and it's also quite expensive to create that plot, because this plot is obtained by doing a lot of independent repeats of the Markov chain for 200 steps, and so it's more expensive to create that plot than to solve the original problem, typically. And so as a result, we don't know exactly, typically, how many steps are guaranteeing that the marginal distribution of the Markov chain is close to stationarity. And so, do we care about unbiased estimators? So in classical point estimation, it's not clear that we do care. In particular, there's, for instance, this quote by Larry Wasserman that unbiasedness used to receive much attention, but these days is considered less important, right? So for instance, less important than mean squared error, which is squared bias plus variance. On the other hand, Jeff Rosenthal in 2000 wrote, when running parallel Monte Carlo with many computers, it is more important to start with unbiased or low bias estimate than with a low variance estimate. So one of the reasons being that by creating independent copies on parallel machines, we can quantify the variance, and we can also reduce arbitrarily the variance by creating more independent copies. However, we cannot quantify or reduce the bias by creating more independent copies. Okay. So in the context of parallel computing, it seems more important to start with a low or unbiased, low bias or unbiased estimator. So in a bit more details, if we have R processors generating unbiased estimators one after the other, there are different ways that we can aggregate the estimators that have been produced after a given wall clock time, t. Right? We can, for instance, discard the ongoing calculation, or we can wait for them to finish, and then we can take an average per processor and then across processors, for instance. There are different regimes that we might be interested in, for instance, the regime where the number of processors goes to infinity, or the regime where the time budget goes to infinity, or double asymptotic regime. And in the late 80s, early 90s, there's been a lot of literature on those different strategies, so how to aggregate unbiased estimators under budget constraints and parallel computers. So for instance, those papers by Peter Glynn and Philipp Heidelberger provide different strategies and different analyses of those strategies. And the starting point is the capacity to generate unbiased estimators. Right? So MCMC out of the box doesn't fit in that framework. So our motivation is to help making MCMC kernels useful in that framework of budget constraint simulations and parallel hardware. So this is a graphical representation of the generation of unbiased estimators, one after the other on 100 processors. This was done on a computing cluster over 24 hours. So each estimator is unbiased for the quantity of interest, but also takes a random time. So you can imagine that there are choices to make when 24 hours are elapsed. Do we wait for the ongoing estimators to be available, or do we discard them? And then what do we do with the resulting estimators? Right? So those questions are not trivial, but they've been addressed by a rich literature that we can leverage if we can obtain unbiased estimators. Okay? So that's the sort of motivation. So I'm going to let John present the proposed unbiased estimators.
Thank you, Pierre. So the essence of the estimator, the unbiased MCMC estimator that we're going to talk about, relies on running two chains that each marginally follow a Markov kernel, leaving the target distribution invariant. And those two chains have to obey a small number of properties. First, that we have to start them from the same initial distribution. Advance the first chain, the X chain, using the marginal kernel. And then for each subsequent iteration, advance the X and Y chains together according to a joint kernel, which has the single kernel as its margins on both the X and the Y chains. The implication of doing this is that at each iteration t, xt and yt have the same marginal distribution. The other very important criteria for our estimator is that this joint kernel has to be such that there exists a time tau where xt and yt minus 1 meet exactly. That might sound like a tall order, but we'll see that in many realistic situations it's easy to create such a coupling of kernels. So the following isn't a rigorous proof, but it's a pretty good heuristic indication of why such a coupled pair of chains might produce an unbiased estimator. It begins really with the telescopic sum expansion. So if we have sufficient regularity on the single kernel such that the expectation of one of the chains evaluated through the test function at a given iteration converges in the limit to the expectation that we're trying to compute. We can express that, we can open up that expectation in terms of a telescopic sum. So adding and subtracting xt minus 1, adding and subtracting xt minus 2, and so on. The key step here is that because we've constructed x and y to have the same marginals at each step, the expectation of a test function applied to xt and the expectation of a test function applied to yt are the same. And so we can replace all of the xt minus 1 terms with a yt minus 1. The other nice thing about this, so if we then are able to pull the expectations back outside the limit, we wind up with a quantity on the inside of this expectation which, if you believe the argument that's sort of hinted at here, should be unbiased for our target. The other nice thing about this is that because we've constructed the joint kernel such that xt and yt meet at some iteration tau and also remain together subsequently, a property that sometimes is called faithfulness, for all iterations after tau, xt and yt minus 1 will be equal, and so those hxt minus hyt minus 1 terms will contribute nothing to our estimator, meaning that we can compute this estimator in a finite number of iterations tau. It's interesting to note that we can also re-express this, or we can think of this as an estimate h of xk, which might be a sort of estimate throwing away a burden of k, plus a bias correction term, which consists of those iterations, those differences from k plus 1 to the time that the chains meet tau. And so this sort of argument is largely due to, certainly inspired by Glynn and Rhee's seminal 2014 paper, which we'll talk about in a little bit more detail later, but which gets sort of the essence of this telescopic sum. So we might also consider, once we've run k iterations of this thing, or once we've run tau iterations to the point where the chains meet, we can create further unbiased estimates by running additional iterations. And generally, it's a good idea to do so from the point of view of efficiency, of reducing the variance and averaging over a larger number of draws. So we introduce a modified version of our estimator, which we denote by HKM, which simply you can think of as the estimate obtained by running to a minimum number k and then k plus 1 all the way up to k plus m iterations, and then averaging over those. So this is simply an average over m minus k things which are unbiased, and so it's self-unbiased, but hopefully with lower variance. We can also re-express this as a very familiar term, which is the average over m iterations to starting the first k as burn-in, plus a less familiar term, which serves as a sort of a bias correction. So this first term is what you would get from a standard MCMC, and the second is what's necessary to ensure zero bias. We'll also see that as k, which is that required number of iterations, that minimum required number of iterations, which sort of plays the role of a burn-in, as k goes to 0, the bias correction, or sorry, as k goes to infinity, the bias correction goes to 0, which makes sense. We've required a lot of iterations to start with on any given chain. And similarly, as m, the total number of iterations, goes to infinity, the bias correction term also goes to 0. So in the limits of a large burn-in or a large total number of iterations, the difference between our estimator and the standard MCMC goes to 0. But obviously in the finite iteration case, there is a more significant difference.
So to give a bit more comments on the relationship between this work and the paper by Glynn and Rhee, which definitely was the starting point really for us on this work. Let's look at the estimator proposed in that paper. So they don't really talk at length about choosing the index k, but let's assume that we take k equals 0 for simplicity. So we'll have h of x 0 as an estimate, plus the bias correction term, which would be a sum up to a truncation, r, which is a user-specified random variable on the integers. Right? So for instance, a geometric distribution. And then the term in the sum depends on the survival probabilities in the denominator of those truncation variables. Right? And so, on the other hand, they do not require that the two chains would meet exactly. Right? They have a weaker requirement that the two chains sort of contract, become closer and closer to one another as the time progresses, but they don't have to meet exactly. And this was also used in the specific context of MCMC by Agapiu, Roberts, and Follmer. So Glynn and Rhee themselves, in fact, have 2 examples in their papers, but none of those examples are MCMC. There's a queuing system example and a non-irreducible chain on the interval 0, 1, I believe. And so the results of both of those papers is that under contraction of the coupling, so if the 2 chains are contracting in a way that the distance between the 2 goes down essentially geometrically, and if we have chosen the truncation variable appropriately means in relation to the contraction rates of the coupling, then we can guarantee that those estimators have a finite variance and also a finite cost. And thus, they can be useful if we can, for instance, have a central limit theorem for averages of independent copies of those estimators. So difficulty is the choice of truncation variable, because in fact, if we don't choose it appropriately, so for instance, if we don't know the contraction rate of the coupling, then it's possible that this estimate would have an infinite variance, but even if we chose it appropriately so that the estimator has an infinite variance, there's no reason why the cost times variance, or the inefficiency of this estimator, would be comparable to the inefficiency of the ergodic average. The ergodic average obtained by running a marginal chain. On the other hand, by those tuning parameters K and M described by John, we will see that we can have a control of the efficiency of the estimator and get arbitrarily close to the efficiency of MCMC estimators in some way. Right. So we're going to see that now in more detail. So the next section is corresponding to section 3 of the article. It contains some theoretical results. The first one is validity result. So we've seen in the heuristic argument a swap of infinite sum and expectation, so it requires a little bit of formalization to make that correct. So the first condition is that the marginal chain converges, so in this sense, in expectation, and also we have some conditions on the 2 plus eta moments of the test function h evaluated on the chain. The second condition is sort of the bigger one. It's that the meeting times have geometric tails. In other words, at most geometric tails. So the survival probabilities of the meeting time, which is this integer valued variable describing when the 2 chains meet with a lag of 1, is upper bounded by c times delta to the power t when delta is less than 1. I'll go back to that assumption in a bit. The third assumption is that the chains are faithful, so that once they meet, they remain identical. Okay, so the third assumption will not be much of a concern because we can guarantee that the algorithms that we're going to look at satisfy this condition. So the strongest condition here is the second one. Under those conditions, the proposed estimators are unbiased, have a finite expected cost and a finite variance. And the proof is very similar to the paper of Glynn and Rhee or article by Matti Virola, for instance. We have another result, and I'm going to go through very quickly, but it's if we're getting a bit tired of this test function h, we can just replace every evaluation of h by a delta mass. Okay, and we find that the approximation of the target is of the form of a sign measure. And if we take averages of this sign measure, we have a consistency result in the article in the form of a Glivenko-Cantelli type results on the marginals of the approximations. So this is proposition 2 of the article. Holds under the kind of similar conditions as the previous result. So the third result is maybe the most important one in practice. It's the one on the efficiency of the estimator compared to the efficiency of MCMC. So for that, we're going to write the estimator as the standard MCMC average with a burn-in of k and a total number of steps of m, and a bias correction term. And then we're going to write the mean squared error of MCMC by MSC. Using Cauchy-Schwarz, we have that the mean squared error of the proposed estimator, which is also its variance, because there's no bias, is less than the mean squared error of MCMC plus terms that involve the second moment of the bias correction term. And so then the proposition that we have, proposition 3 in the article, controls the second moment of the bias correction term under some conditions. So for instance, geometric drift condition, which will be recalled in the next slide. Some regularity assumption on test function h, a bit stronger than the ones used in the validity result. Under those conditions, the second moment of the bias correction term decreases geometrically in the index k and polynomially in m minus k. And that's important because it means by increasing k or increasing m minus k, we can get that second moment to be very close to 0, and thus we can get the mean squared error of the proposed estimator to be very close to the mean squared error of the standard MCMC estimator. Okay. So the last result is a result that allows the verification of this strongest assumption, the fact that the meeting time has geometric tails. So the proposition goes as follows. It's proposition 4 in the article. It says that if we have a drift condition, so here I'm going to state it explicitly, there's a function v that maps the state space to 1 infinity, lambda between 0 and 1, and a constant b, and a small set C such that if the chain is outside, marginally if the chain is outside the set C, the expected value of the function v decreases by a multiplicative factor lambda. The small set C is of the form of a level set of the function v, with a level satisfying a condition with respect to lambda and b. And such that if two chains are in the small set C simultaneously, when that's the case, if there's an epsilon probability of the chains meeting at the next step, then in fact the meeting time will be such that the tails are geometric. Okay. So that's convenient because drift conditions have been identified for a variety of algorithms. And so if we have a drift condition and we further prove that the small sets for which the drift condition holds are such that there's an at least epsilon probability of the chains meeting, then we'll have assumption 2 of the main results being satisfied. Okay. So in other cases, it could be that you can directly verify this assumption 2, but this provides one way that might be convenient if you already can rely on a result on geometric drift conditions. Right. So John will now present some concrete examples on how to couple MCMC algorithm in order to use them in this construction of unbiased estimators.
So the key ingredient that we haven't discussed so far is how to couple two Markov kernels such that the chains meet exactly in a time with polynomial tails. And we'll see that for many common algorithms, and in detail for Metropolis Hastings and a little less detail for Gibbs, it's usually very straightforward to construct such a coupling. So what we'll do is, and I should mention that this question of couplings is one that is extremely classical, in which there's a rich variety of tools available to us, many of which we use and stitch together in different ways for these examples. So we'll say that two random variables x and y follow a coupling of a law p and q if marginally x is distributed according to p, y is distributed according to q. And there's a nice inequality that comes up all the time, that the probability of obtaining x and y that are matching exactly is upper bounded by a term related to the total variation distance between p and q. So in particular, since we're looking to get our two chains to meet, we'll often be looking at couplings that in some way involve a maximal coupling, because if we could maximize the probability of meeting, in most cases that's what we'd like to do. So under the heading of a rich variety of couplings, even for two multivariate normal or even univariate normal random variables, we can think of a pretty large variety of them. The most obvious or straightforward one is an independent coupling of x and y. We can also consider optimal transport couplings that minimize the expected square distance or other distances between the random variables. In the case of two univariate normals, this can be constructed very simply by drawing an epsilon that's normal with mean 0, and then offsetting it by the mean of x to obtain x, the mean of y to obtain y. We can also consider reflection couplings, which follow the same procedure, but flipping the sign of epsilon for y. And finally, we can consider various flavors of maximal couplings that at least attempt to get an exact match between x and y, and then do something else in the case that a match isn't possible. Two great, not recent but excellent references on couplings are the book of Thoresen and Linvall and Rogers, or the paper of Linvall and Rogers on this. So just to run through quickly what these couplings look like, the independent coupling of two univariate normals has a familiar look. We can see that the optimal transport coupling and several of the other exotic couplings here occupies a sort of a lower dimensional manifold. We can see that one-to-one mapping between points in the distribution of x and distribution of y. A similar qualitative impression comes from the reflection coupling, only now we're mapping points on the extreme right tail of x to the extreme left tail of y, and vice versa. And an interesting coupling for our purposes is this independent maximal coupling, which attempts to get a maximal coupling between x and y. And in the case where that is impossible, draws independently from the what you might call the residual distribution of x and the residual distribution of y in order to obtain the correct distributions marginally for both variables. Perhaps a final coupling is what you might call a reflection maximal coupling, which attempts the same maximal coupling between x and y, but then in the case of not being able to use the same point for the two, takes a reflection of the law of x, of the draw for x actually, to be the draw for y. And a distinction which isn't obvious when we're coupling, say, one-dimensional normals, but plays a very significant role in higher dimensions is that whereas the independent maximal coupling introduces sort of a full-dimensional noise in the case that the same point can't be used for x and y, the dimension behavior of the reflection maximal coupling is much more favorable. And anyway, we'll see dramatic examples of that later. So back to Metropolis Hastings. We have a variety of means at our disposal to couple normal random variables. If we want to couple two Metropolis Hastings chains, there's an easy recipe for that, which is that we draw proposals from a coupling of the proposal distribution for x and proposal distribution for y. We compute the acceptance ratios. We use a common uniform random variable to decide whether to accept or reject the draws on x and y. And then if all has gone well, we've proposed the same point for both chains and accepted it, in which case we have a meeting. And if not, we have two new points that are marginally from the correct kernel, and we try again on the next iteration. So, all right. So, just on a very simple toy example, with a standard normal target, proposal variance 0.5 squared, and an initial distribution centered at 10 with variance 9. We can see that we obtain meetings in a relatively small number of iterations. There's a spike where the chains meet very soon after initialization when they're both close to 10, with a longer tail as the two chains approach the mean of the distribution of the target. We run this estimator with a k, so with a minimum number of estimates, or a minimum number of iterations of 200, and an m, so a total number of iterations of 1,000. And we see that the average cost to assemble this estimator is 1,048, meaning that we mainly are running the single kernel after the two chains have met. If we compute a measure of the inefficiency, so combining the variance of the resulting estimate scaled by the cost to obtain that estimate, we see that with this simple setup, the inefficiency is about 30% larger than that of standard MCMC. Something obviously that we could reduce by either increasing k or increasing m. So a much more interesting example comes with a multivariate normal target. Here we take a normal centered at 0 with a covariance matrix, which is either, in the simplest case, a diagonal, or in more interesting cases, a covariance matrix that's sampled from either an inverse Y-chart, so a dense covariance matrix, or a sparse one created according to this formula. What we see is that the independent maximal coupling based Metropolis Hastings, although it yields valid estimates, delivers pretty abysmal performance with dimension. So the average meeting time is plotted here on a log scale, and the dimension just goes from 1 to 5. So already by dimension 5, with a simple mean 0 diagonal covariance matrix normal target, it's taking tens of thousands of iterations. So in practice, both for efficiency reasons and for time cost reasons, this coupling becomes infeasible very quickly. What's interesting, though, is that with the reflection maximal coupling of proposals, so a coupling that, again, attempts to get x and y to meet, and failing that, uses reflected draws for y versus x, we actually obtain very favorable scaling and dimension. It's not quite linear, but it's something closer to d log d in the dimension d. So with this, we can see that although the coupling is superficially similar, the performance is much better in dimension and can handle realistic problems. So I'll pass just very briefly over Gibbs. An easy way to couple Gibbs when we have couplings of the conditional distributions at each sub-iteration are to simply couple those conditional distributions, and the two chains will have met when we obtain meetings over an entire sweep. Obviously, if we obtain meetings on some of the variables, it may be helpful, but it doesn't result in the chains having properly met for the purposes of this estimator until all of the parameters have met. We can see that this produces relatively different behavior on this multivariate normal target depending on the properties of the covariance matrix. So the inverse Wishart covariance matrix is quite challenging and results in relatively quick increase in the meeting time as a function of dimension. Whereas the geometry of this exponential covariance matrix is extremely favorable for the Gibbs and yields distinctly sublinear scaling and dimension.
So now we're going to look at some other examples that are essentially in section 5 of the article and also in the supplementary material, and then some of the points of the discussion in section 6 of the article. So I'm not going to focus on one particular example, but instead going to say a few words on each of the example and why we chose to include those examples in the article. So the first one is a univariate bimodal target defined as a mixture of two Gaussian. In itself, it's a pretty simple example. We use it for two purposes. The first one is to highlight the effect of the choice of K and M, and numerically validate that increasing K and M, we can obtain efficiencies close to the efficiency of the underlying MCMC algorithm, which is random walk Metropolis Hastings here. And we use that example to highlight another phenomenon, which is that observing short meeting times can sometimes be misleading. So in particular, if we tune the algorithm such that it's difficult for the chains to explore both modes, to go from one mode to the other, and if we start the chains systematically in the basin of attraction of one of the two modes, then we're going to observe a lot of short meeting times until maybe after the millionth attempt, we're going to finally see one of the two chains going to the other mode before meeting the first one, and then we will see a very large meeting times. which will effectively change everything we think we know about the distribution of the meeting time. So it's an example of how the results can be misleading. It's not because we have an unbiased estimator that 1,000 IID copies of it is enough to provide accurate results, right? In certain cases, you might be enough. In other cases, you might need to run many more independent copies. The second example is a classical example, a Gibbs sampler for the so-called nuclear pump dataset. We chose that example because that was one of the examples in the paper by Miklan, Tierney, and Yu on regeneration methods, which provide another framework, very compelling in many ways, of parallelizing MCMC calculations. And so we wanted to sort of revisit the same example and do a comparison between the proposed approach and the regeneration method. A third example is a Ising model on a 32 by 32 square lattice with different inverse temperatures and periodic boundary conditions. And we look at single-side Gibbs samplers and parallel tempering as well. So for the coupling of parallel tempering, the two chains each are made of multiple chains, so to speak. So there are ensembles of chains, and they meet if every single member of the ensemble matches with the corresponding member of the other ensemble. And we look at the effect of the number of chains in the ensemble and also the effect of the inverse temperature. The fourth example is a variable selection problem. So the state space is the space of binary vectors of length p. And we tried with p up to 5,000 in synthetic data sets. And we use an algorithm that is studied in Yang, Wainwright, and Jordan. And in that paper, they show that the mixing time of the algorithm scales linearly with p. And so numerically, we observe that the distribution of the meeting times divided by p looks like it's stable. So informally, we also sort of get similar results for the meeting times as was previously proven for the mixing times. I should say in all the Gibbs samplers, the coupling strategy is simply taking every single conditional updates and doing a maximal coupling of those updates. So it's very systematic and certainly not optimal way of coupling those algorithms. The fifth example is an example motivated by a paper by Martin Plummer in 2014 describing the cut distribution, which is an alternative to the Bayesian posterior distribution in the setting of a model made of different submodels, and where we might want to propagate the uncertainty from one model to the next without allowing feedback. So it's a departure from standard Bayesian inference. And it's a distribution that is a distribution on the joint space of all the parameters. That is not the Bayesian posterior distribution, and that is, as explained in the paper by Plummer, challenging to approximate with standard MCMC methods. And we use that example to illustrate an appeal of the unbiased property that is not to do with parallel calculation, but instead an appeal that comes from the nice interplay between the unbiased property and the law of total expectations that allows to approximate those cut distributions. So the supplementary materials contain the proof, some discussion of Hamiltonian Monte Carlo, which has been looked at in more details in a paper with Jeremy Heng. And also the following example. So there's a Gibbs sampler, also very classical example for the baseball batting averages data set. And we look at this example because Jeff Rosenthal in 1996 paper has established that analytically that after 140 steps, the marginal chain is 1% away from stationarity in total variation. So we were curious to see how the meeting times compare to 140, and we obtained over 10,000 repeats that the meeting times were systematically less or equal than 4, for instance. The second example, it was actually the first example that we looked at with John and Yves. It's a coupling of the polyagama Gibbs sampler, and we sort of looked at it for the wrong reasons. We initially thought that those methods would only apply to uniformly ergodic Markov chains, after having worked with Frederick Linston and Thomas Schoen on the case of conditional particle filters. And so we thought, what other MCMC algorithm is uniformly ergodic? Well, the polyagama Gibbs sampler. So that's why we looked at this reason before realizing that we didn't require the underlying algorithm to be uniformly ergodic. And the last example is a Gibbs sampler for the Bayesian lasso regression of Park and Casella, where we look at the impact of the regularization parameter. So as it turns out, in that example, the difficulty is less to do with the dimension of the state space than with the data set that we have, actually, the sort of signal-to-noise ratio of the data set, and also the choice of the regularization parameter. And that has to do with the impact that those things have on the marginal mixing of the Markov chain. So I'm going to just raise a few points for discussion, following, again, the discussion section of the article. The first one is that we argue that this technique of coming up with unbiased estimator applies to a variety of settings. And I would say with sort of minimal effort. So for instance, for many Gibbs samplers, we've simply taken every conditional update and applied a maximal coupling, for instance, a rejection sampler maximal coupling, which sort of applies out of the box. The couplings are algorithmic specific. So if you come up with a new MCMC algorithm, you'll have to think about how to couple it, but they're not target specific. Right? So for instance, for the random walk metropolis hastings algorithm, we propose to use a maximal coupling of the proposal distributions. And that doesn't require knowing anything about the target in particular. We don't need to know about a set where most of the target distribution puts its mass, or we don't need to know a maximal value of its density. And that is in contrast with some of the regeneration methods that we've come across. So for instance, the Brockwell and Cadane work provides a pretty generic framework for regeneration, but still requires knowing something about where in the space the target puts its mass, or what value the target density is on that set. So it's not necessarily easier or harder, but it requires thinking about different things compared to regeneration methods. The choice of the parameters, K and M, and we could also throw the lag in the mix. The paper uses a lag of 1, but we can think of using another lag between the two chains. Those are tuning parameters of the method. They strongly impact the efficiency, so they need to be chosen carefully. This is something that we discuss in the paper, but we're hoping that there is more things that can be said about this choice. Even for fixed choice of K and M, the algorithms themselves, the MCMC algorithms, have their tuning parameters. And there's no reason to believe that the optimal values of those tuning parameters would be identical to the optimal values that have been identified for the marginal MCMC algorithms, right? Especially under budget constraints. For instance, for random walk metropolis hastings, it might not be the case that the known optimal acceptance rate is achieved with the same parameters that would be optimal in terms of minimizing the expected meeting time. Fourth point is that if you start with an MCMC algorithm that is ill-suited to the target at hand, so for instance, an algorithm that struggles to explore multiple modes of a multimodal targets, then since marginally none of this construction helps mixing in the chains, we will also miss the same modes, so to speak. Right? So the methodology requires starting with an MCMC algorithm that is appropriate for the target. So it certainly does not, it's just another way of using MCMC kernels than applying the kernel many, many times in a row and taking the ergodic average. But there is still the same questions about which MCMC algorithm is best for any given target distribution. Another point is that the meeting times give some information about the mixing time. So explicitly in the discussion section, we have this upper bound on the total variation distance between the chain at step t, pi t, and the limiting distribution pi, in the form of an expectation of a function of the meeting time. We followed up on that with Niloy Biswas and Paul Vanetti in a paper in 2019 where we provide upper bounds on the total variation and on the 1 Wasserstein distance. Of course, if we had access to perfect samplers, it would be better. We'd have unbiased estimators, but also more. In particular, we'd have estimators that take value in the range of the test functions h of interest, which is not the case for the proposed unbiased estimators. And finally, beyond the use of unbiased estimators for parallel calculations, the unbiased estimators might have other appeal. We illustrate this for the case of the cut distribution, but we're wondering if there are also other cases where one might care about unbiased estimators, but not for parallel computing reasons. So this work was supported by 3 grants for the National Science Foundation, for Yves and myself. And those are some further references, and the code for the article is available on GitHub, and some entries on related topics are regularly posted on this blog. Thank you very much.
Okay, first of all, obviously I'd like to thank the authors for this extremely interesting and thought-provoking paper. I've very much enjoyed reading it and thinking about it and playing with some of the examples. So just to very briefly put things back into context, the problem is really addressing the burn-in issue for MCMC, right? So we know that because we can't typically easily sample exactly from the target we're interested in, we rely on our MCMC methods to converge to equilibrium, but it's really hard to diagnose that burn-in and convergence process. So what the paper doesn't do is try to tackle the exact sampling problem head-on, which we know is an extremely difficult problem. Instead, what it does is it corrects the bias in any sample-based estimates that come out of the algorithm. And that turns out to be much easier, but also potentially really quite useful. So just to emphasize, the approach is really quite general. It could be used in lots of different settings. This paper concentrates on Metropolis Hastings and Gibbs sampling, and so I will concentrate on that setting too, but as has been mentioned, people are exploring this in lots of other contexts as well. All right, so I've got some materials online for this if anyone's interested, and I'll give that address again at the end. So here it is for a simple Metropolis Hastings chain. So this is the basic idea. You run 2 chains in parallel. You encourage them in some way to coalesce, and once they coalesce, they stay coalesced, and that allows you to construct these unbiased estimates of quantities of interest. There's this slight wrinkle that you want to couple them with an offset of 1, but that doesn't really cause any problems other than making the code a little bit more fiddly to write. Okay, so a really key result in the paper is this time-averaged estimator. And so, as was mentioned in the main presentation, it essentially takes the form of the estimate that we're all very familiar with already, together with this bias correction term. And of course, this bias correction term is sort of, in some sense, in principle infinite, but because of the coupling involved, it terminates after the chains have coupled. So it is something that we can evaluate in finite time, and so this is very attractive. And there's kind of this underlying sort of association between the chains coupling and convergence of the Markov chains in some sense. And it's very tempting when reading the paper and thinking about these algorithms to blur the distinction between the two things. But actually, it's really important to keep in mind the fact that they're not the same thing, okay? You can have chains that mix really well and converge very quickly, but actually you have a terrible coupling, and so it takes a long time to couple. That would be perfectly possible. And vice versa, you could have a chain that mixes very badly, where burn-in is a serious problem, and yet nevertheless engineer a small coupling time. But as was mentioned in the main presentation, although it's really tempting when you look at these, this kind of result to think that clearly it would be good to engineer a very short coupling time, and you can do that, right? You can initialize the chains from the same point. You can use Metropolis kernel to hopefully stay in that position even after your offset of 1. Okay, so engineering early coupling is certainly something you could do, but it might not be a very safe thing to do, as was mentioned in the main presentation. All right. So, obviously this technique works for coupling Metropolis Hastings samplers. It works in the multivariate case as well, but somehow when we got big challenging problems, we nearly always end up resorting to some kind of component-wise update. Okay, so the standard example of that will be something like a Gibbs sampler, and so we can think about how to use this coupling idea in the context of Gibbs samplers with very large numbers of components. And as was mentioned, one way we can do that is simply by coupling the full conditionals in your Gibbs sampling algorithm. And so simply you then have to wait for all of the components to coalesce, and then you have a coalesced chain. So that seems like a good idea, but I think it's probably fair to say that there's not much theory in the paper that really gives us a sort of strong reassurance that this will actually happen in reasonable time in practice for challenging problems. So it's quite interesting to think about, well, does it? And actually the results are reasonably encouraging. So to start off with, keep it simple. Think about a simple AR1 process. So we can have a little Gibbs sampler for an AR1 process. Obviously, we can exactly sample from this process, but let's just imagine we want to do a one variable at a time Gibbs sampler to sample from the full conditionals of our AR1 process. So we just run through each variable in time, in turn, sampling from the coupled full conditionals for a pair of chains, and we see what happens. Okay? So when we do that, here, just so you know how to read these plots, the vertical axis is space or time in your AR1 process, and the horizontal axis is iteration number of your MCMC algorithm. And if you look at those two chains, you can see they look very similar, especially on the right-hand side, so it sort of looks like they've coupled, okay? So obviously you can look at the actual coupled variables, okay? And you see plots like this. So how to read this plot, the dark red are the variables that have coupled already, and the light color variables are the variables that are not coupled. So you see it starts off not coupled. Actually, you get pretty rapid coupling behavior, but you get this little pocket that isn't coupled, and it certainly isn't true that once variables are coupled, they stay coupled and they never uncouple, right? You can see this is very much a stochastic process, but eventually there's sort of the two chains are sort of getting squeezed together. They're getting gradually more and more coupled, at least stochastically, till eventually they couple, and obviously once they're fully coupled, they stay coupled indefinitely. So obviously we can repeat that process and see what happens. And for this simple AR1 example, you see that here for these 6 realizations, 2 of them had failed to couple even after 500 iterations, but generally the overall pattern is that these chains do coalesce eventually. They do gradually get dragged together. The coupled variables sort of pull the other variables together in some sort of weak way, so that eventually they will squeeze together, they will coalesce, and the chains will couple. Okay, so I wanted to look at a slightly more interesting example, slightly more challenging. So I thought I would look at a Gaussian Markov random field, just a 4-neighbor version on a regular lattice with periodic boundaries, and see what happens there. So here I did it on a 150 by 150 grid, so a nice big example with obviously over 20,000 variables. Still a simple one variable at a time Gibbs sampler. Again, we can sample from this exactly, but I wanted to see how the Gibbs sampler worked. And actually, in many ways, it worked better than the AR1 example, which I was slightly surprised by. So here, I'm going with an autoregressive or conditionally regressive parameter alpha here of 0.99. It's interesting to see how bad things get when you do choose the improper case of alpha equals 1. Obviously, that violates lots of assumptions in the paper, etc. But it's kind of interesting to see how things can go wrong if you're not a little bit careful. But in the alpha equals 0.99 case, we can look and see what happens. So here's our Gibbs sampler for our Gauss-Markov random field. So that's not very interesting, that's just one of the components. The more interesting thing is looking to see what happens with the coupled variables, okay? So here this is now binary, the black represents coupled, and this image, obviously it looks very much like an Ising model type image. So in some sense we're looking at sort of the annealing of an Ising model, and it'd be kind of interesting to think about whether that could give useful insight into the coupling behavior. Just very briefly, the maximal coupling mentioned in the paper and the reflection maximal coupling work very similarly for univariate full conditionals. Obviously, the reflection coupling is designed for multivariate proposals. It's not totally obvious that it would necessarily be better in the univariate case, but in my experiments, it was not worse ever. On Gibbs sampling problems. The other thing I wanted to say briefly before finishing is this application to parallel chains, right? So this is one of the key motivating factors. So the idea is that unbiased estimators can be safely averaged, but this debiasing doesn't eliminate the burn-in. And one of the problems with parallel chains is that you end up having to repeat the burn-in on every processor. And so although the method in this paper clearly helps, because it allows you to sort of safely average unbiased estimators, maybe allows you to be a bit less conservative with your choice of burn-in, you still have the fundamental parallel chains problem that you repeat the burn-in on every processor. And so if you think about having a sort of a burn-in plus a nominal run of length n, the amount of speed up you can get, even as the number of processors goes to infinity, is bounded, right? And so there's no fundamental way of getting around that. Every process you run is burning in, and that is fundamentally limiting the effectiveness. So, in summary, this is a really interesting paper. I very much enjoyed thinking about it. It's definitely interesting in the context of parallelization. There's loads of open questions to do with the sort of co-development of coupling algorithms and MCMC algorithms, and how you trade off easy coupling with good coupling, good efficient MCMC kernels, etc. So overall, very interesting and discussable contribution to the literature, and it gives me great pleasure to propose the vote of thanks.
So, yes, I'd like to say thank you again for Pierre and John coming here, talking and providing an interesting, really interesting paper to get my teeth into, have a look at, have a go at coding. Now, some of the points I was going to make, actually, Pierre has already answered, either during, and John during the talk, or in fact, chatting to him beforehand. So, what I'm going to talk about, I'm going to give a slightly different intuition on how the method works, which will point out the sort of role of noise in it. Some of the suggestions and connections to the literature, I now feel I don't actually need to make, they've already been made. And I'd like to detail, like Darren did, a few experiments I conducted and insights that may come from that. So we actually don't really need to talk about this. So let's go straight into a very simple estimator. So what I've got here is two chains, the x and the y. The x is in black, the y is in red. The coupling time is tau here, and let's say, for sake of argument, we pick k here. Okay, so that's fairly early k, but I just want to use it to explain what's going on. Now, in a way, this is reverse engineering the argument that proves it's unbiased. Okay, so we've got this estimator. Let's just go for the simple estimator to start with, hk. It's h of xk plus another term, and clearly h of xk, if we make h the identity, then h of xk is very, very biased. It's up here, and we know the truth is somewhere down here. Okay, this is normal 0.50, and we've started way up here. So what's going on with this, the rest of it? From k plus 1 up to tau minus 1, we're looking at xj and yj minus 1, subtracting the differences. Now, xj is typically started, xj is one step ahead of xj minus 1, xj is also one step ahead of yj minus 1. So, on average, there's a behavior where they're both drifting down towards the equilibrium distribution. And on average, xj is one step ahead down that drift compared to yj, or yj minus 1. So you're adding up essentially a load of negative differences, which on average will take you down to here, which is where you want to be. Okay? But already you can see, all right, the red chain is not always behind the black chain. Yes, there's a lot of noise. There's noise all the way down. The differences are negative, they're positive, they're negative, they're positive. And when you've hit approximately stationarity, not exactly obviously, but approximately, then you're purely adding on noise. Almost purely. I take that back. Almost purely adding on noise. Okay. So that's the estimator. So basically, roughly speaking, most of the bias correction is happening in this first bit, what we would call burn-in. most of the real bias correction, but there's also noise there. And then for the rest of it, it's a teeny bit of bias correction and a lot of noise. So we want to reduce the noise, and if we can possibly do it, mostly couple the change, almost as soon as they have hit this almost stationary place. So the averaging estimator that's introduced, that certainly reduces the noise. You're averaging over a whole lot of the same realization, but a whole lot of terms. So essentially, I should say, that's taking this green line and moving it further and further all the way up to your final point. Once you get past here, there is no bias correction term. Okay. So that's that. If you think about, now this is not strictly a correct thing to do, but imagine conditioning on this particular tau value and looking at all the chains you happen to run that would meet that tau. If you look at what the variance of that would be, a back of the envelope calculation tells you, well, oops, if tau is bigger than your k plus 2, then, sorry, smaller than k plus 2, it's 0, because the term is 0. But otherwise, it's actually proportional to tau minus k, so your burn-in time minus your coupling time minus your initial value, burn-in point, cubed. And you're divided by m minus k squared. So obviously that certainly means we want to make tau as small as possible, and the reflection coupling of Bourabi et al. Really helps. So as you said during your discussion, during your presentation, the standard method is just really bad as dimension increases. I also wanted to make the connection to the diffusion coupling and the Lin-Ballum-Rogers, which you now said. There's also something, by the way, that's called projection coupling, and I wondered if you'd tried that, because that's also in the diffusion, the coupling diffusion literature. It's a very similar idea. I wonder if it was better or worse. And also, which the recommendation in the paper was choose k so that actually this term is mostly 0. Your bias correction term is mostly 0 because it's the 99th percentile. So initially when I first was looking at the paper, this recommendation of 99th percentile seemed fairly extreme, but actually, as I saw in the experiments, no, it's the kind of minimal. And you want to choose m so that when this term's non-zero, this bottom term dominates, so that the whole thing's not too large. So this is the point about choosing an m that's like 10 times k, or 20 times k. So the example I'm going to look at is a 20-dimensional target where the variance in the kth dimension is k squared. It's diagonal, and I'm starting at an offset which is 10 standard deviations off in each component. And I've just given you 4 of the components, so I ran it for 100,000 iterations. This is the first component, which is going to mix really thoroughly. This algorithm is tuned for the optimal random walk if it's got a lambda squared times the identity proposal. This is the 20th dimension, and it's kind of the minimal you would want to see for an MCMC chain that you want to actually use to estimate things. 100,000 iterations. And we're going to just focus on this last one, which is the hardest component to estimate. So this is the coupling time. This was using the Bourabi thing, obviously, otherwise coupling time would be absolutely enormous. From 5,000 simulations, and what I've got on the x-axis is log base 10 of the coupling time. Okay, so it coupled mostly between 100 iterations and 10,000 iterations. Right, let's look at the bottom. So this is again log base 10 on the x-axis of, k. So what I'm doing is different to what Pierre did in the paper. I'm saying your m is fixed at 100,000 iterations. That's what you've got. How does the estimator behave as you increase k? And I start k at 100, and then gradually increase it through 1,000, 10,000, up to 50,000. Now, in black is the estimator from MCMC, right? If k was just your burn-in, then what happens is at 100 iterations you've still actually got part of the heading down to stationarity. Then it gets better, and towards the end, because you're actually getting rid of half of your 100,000 iterations, it gets slightly worse again. Here is the mean, so this is mean squared error, I should say, and again it's on log base 10 scale. Okay, so the mean squared error here is a bit under 1, so 10. Here is the estimator. So this is using k equals 100, and I'm using 100,000 iterations. Thank you. Okay. And initially, when you're allowing all the taus to still be there, we're at, what's that, 100,000 mean squared error. And in fact, let's put that here. So these are the quantiles of the taus. So the quantiles of your meeting time. This is the 99th one, which is what's recommended in the paper. Mean squared error is still 10,000. 0.991, it probably reduced quite a lot to maybe 1,000. And basically the best thing is if you can choose it so that it's not going to exceed it. Looks like I was running out of time. I did try another experiment, which was counter to my intuition and the intuition in the paper. What if you start them at the same point? And you can actually see you get, this is similar to what the slide you showed earlier, you get a mixture distribution. They can couple quite early on, or you get the same distribution as previously. Yeah. Interestingly, this is the mean squared error plot, and it does actually make things better this time because you've got this mixture distribution. It seems like the noise is outweighing the extra bias correction terms, the sort of average size of your bias correction terms that you've got. So that was interesting that it does reduce the mean squared error a bit. I had better go to my summary. So it would be interesting to see a comparison with the other techniques. So there's a comparison in terms of when they're usable, and the other techniques, the random truncation techniques, are harder to use properly. It would be still interesting to see a comparison in efficiencies. It seems to me that this noise in the difference between the two chains, because you're just using two chains here, two chains there, can be an issue. Obviously, with enough cores, you would reduce that as much as you want. It feels like, even though it reduced it in that particular example, and that was 5,000 simulations, it shouldn't be sensible to start with x naught equals y naught, but it seemed to work then. In fact, what seems more sensible is to try and start from an over-dispersed. So x and y negatively correlated and maybe sampled from the prior. On the plus side as well, this was really easy to implement. Yeah, it's not much harder than standard MCMC to implement. When I first saw the title of the paper, I thought there would be some kind of minorization conditions you had to deal with in there. In the actual implementation, no. And I found it interesting. It certainly does seem potentially useful, especially for embarrassingly parallel MCMC. So I am very pleased to be able to second the vote of thanks to the authors.
Well, I first want to really congratulate my colleague Pierre and John and Yves for really reigniting this great interest we had 20-some years ago about perfect sampling. And many of you, if you still remember at that time when the Popper-Wilson algorithm was proposed in 1996, we were all getting very excited. We thought we're going to solve the Monte Carlo problem MCMC forever because who's going to use anything else? And it turned out to be not as exciting as we all believed because I think a part of the problem, and I blame, they had a bad name. They called coupling from the past. You know, it's just not very exciting. What we need is a coupling for the future, and I think we probably see one today. But I do want to. My discussion here is really. I'm really inspired by their work, and I want to make a connection to the coupling from the past. And I hope that we do offer something for the future together. I also like their term called unbiased MCMC because these days it's very hard to get unbiased opinion, particularly on the eve of the election, and you guys know what I'm talking about. What we discovered, I would rather notice, there's a very simple re-expression of what they proposed that provide a different interpretation and it leads to a different, a slightly modification that you see can actually do, sometimes can do better. So this is their estimator, as we have seen many times. But you can rewrite this estimator in the following version. instead of start from xk, you move forward, you can starting from the going backwards, okay? Now, the difference is that, and I call the first one, especially with tau bigger than k plus 1, the first one that everybody talk about is a forward correction. It's correcting the bias, say xk is not unbiased, so I had adding these noises as previous speaker just talked about. But if you look at the second one, it's actually a backward correction. You're already at the stopping time, and then you say, well, we know that's not exactly unbiased either, although for those who still remember proper Wilson's read the ones forward coupling, you recognize why it's tau minus 1, not tau. You need to go back once, and when you do the forward coupling, it was perfectly done, but here's not perfectly done, but you will see there is this term. I don't know if does it work. So you will see that essentially is correcting backwards. But the key is to observe in this correction backwards, every term there actually has mean 0. Now, but that does not make the sum mean 0. This is the interesting part, because the tau depends on the x. Okay? So it's a random number of averages, but each term is unbiased. So it's very much like previous speaker was talking about. There are lots of these unbiased ones going backwards. What they're doing is to determine how many of these terms are needed. But what's the insight here? Well, the insight here is that because you have these unbiased terms, I can use control variates. I can add on things that are unbiased. Unbiased for 0, you're still going to get the unbiased estimate. So here is a proposal. Right? Take the delta as a difference, okay? And it doesn't mean exactly 0. Now what I'm doing, I'm going to take any eta that is independent of the original chain. It could be a constant. It could be anything else, okay? And then if you add that to it, right, their original estimator plus this term, it will be still unbiased, okay? It's by definition. But now I create an entire class depends on choice of eta. So at least I can try to optimize over eta, I can do better. That's what the whole swing idea, control variates idea is. And in fact, I don't have time to talk about, this also leads to the L coupling, different inequality, different bounds. You can do all those things. What's interesting here is that you can see why this might work, especially if the tau is large. I sort of have another hour, sorry. But the idea here is you can see, if you choose tau wisely, you're going to cancel these corrections. You're going to cancel lots of unnecessary ones. The preliminary series says that probably the good choice is the median of the stopping time. You see, it's a plus minus, that kind of stuff. But if you do that, and so how do you run it in practice? Because you cannot have the eta estimated by its chain self, but if you run in parallel, it's trivial, right? You get the median from the rest of the chain. So all you do is the following, right? You run parallel chains, each one of them is just like what Pierre suggests. Then you take the eta is the median of the rest of the chain, and that creates independence. Then you just average them up, and this is the time average version, exactly doing that. So what we do is we make the comparison with the one which you simply do each one and average of them, okay? And the beauty of this thing, I think on average, you're not doing more function evaluation because half of them you already evaluated because of those things. Now, he's asking to stop, so I'm going to stop in the best slides. Okay, so this is just simply doing, using the pound failure data, 2 chains, 5 chains, 10 chains, no time averaging, all these different parameters. You see that the star is the one doing this control variance. You see the reduction of the variance uniformly. Now, the reduction of the variance disappears quickly when you do time averaging, okay? Partly because everything you're adding on, essentially law of large numbers kicking, you have many of the zero terms. But what's really important is because when the tau is large, that you have more gains. If a tau is small, there's not much gain. So what we did is quickly we run another simulated examples from the same POM data using their model with a slightly more running time. And then even with the time average, even 70, you will see some reduction. So I think the gain here is really when you have the large large tail. And if there's no cost, why not doing it? And I want to say that initially I would have really take another hour. There was another slide I decided to cut last night. We used this to prove all these bounds, these L bounds. We got the different bounds for the total variation distance. And we show the bound always, not always, most time beats the bounds you have, except I proved last night, whenever I beat you is when both bounds are trivial. So I'm not presenting. But they're definitely something that I will show you later. Thank you.
Great. Well, firstly, thank you ever so much to the authors for a great paper and a really interesting talk just now. So this discussion is joint with Murray Pollock, Gareth Roberts, and David Steinsaltz. So as has been mentioned several times already, regenerations are closely related to couplings and the kinds of problems that are being addressed here. So for example, couplings have been, regenerative methods are used to deal with bias and also parallelization. And some of these works go all the way back to 1995 with the Micklin paper, which has been mentioned already. And so in this discussion, we just want to highlight some recent advances in studying regenerative methods, in particular in continuous time, a method we've called the restore sampler. So this is a continuous time regenerative sampler. So we're working in continuous time, and we want to build a sampler which innately possesses regenerations. And this has three core ingredients. So firstly, really the law of a continuous time Markov process, YT, which defines the inter-arrival dynamics. Secondly, a locally bounded function kappa, which will be the regeneration rate. And this will essentially define a Poisson clock. And when this clock rings, we'll look at number 3, which is a fixed probability measure mu, which is the regeneration distribution. And so essentially, the idea is you run this inter-arrival process Y with a clock attached to it. Whenever the clock rings, you redraw its location from this fixed regeneration distribution mu. And that's essentially what it does. So it's a kind of a mixture of these two, a local dynamic and a global dynamic given by these regenerations. And the name is a bit silly, of course, but it's randomly exploring and stochastically regenerating, so restore. And the resulting process, it's a continuous time Markov process. It's non-reversible because there's a sense of direction of time. It's rejection-free, although in continuous time, that's really with a bit of a star. And it naturally possesses regenerations. Whenever this clock rings, that is itself a regeneration time. And so here's just a little animation to give you a sense of what it might look like. So this is simply a univariate example targeting a bimodal distribution. And so here, the inter-arrival dynamics are, of course, continuous time. But you can just take a discrete time Markov chain, embed it in continuous time by using holding rates. So here, there are constant holding rates. And the regeneration distribution mu is just an over-dispersed Gaussian, and you can just do something like this. So the points on the left are flashing green and red. So red means a regeneration event, and green just means it's propagating according to the local dynamics, which are just a simple random walk metropolis. And of course, this is a toy example, but it just gives you a sense of this interplay between the local and the global dynamics. And while there are no rejections, as you can see in the middle, there are often these very short lifetimes, which kind of are essentially rejections, although technically they're not. And another point of connection between this work and, so in many settings, the point is you choose this regeneration rate kappa in such a way that the resulting process possesses, of course, pi as its invariant distribution. And so this gives, if you like, a general recipe to combine local dynamics Y with global moves in such a way to enforce pi stationarity through regenerations. So it really is this regeneration mechanism which itself is correcting the bias, if you like, of the underlying process. And so another point of connection, so CFTP coupling from the past has been mentioned numerous times already, and I'll mention it one more time. And of course, I guess we all know it's an elegant technique to get an exact draw from the stationary distribution of a Markov process. And in particular for the restore process I'm mentioning now, coupling from the past can be done very easily in principle. Because if we're in a situation where this regeneration rate kappa is itself uniformly bounded below by a strictly positive constant, then you can imagine what's happening is no matter where the process is in the space, at a rate epsilon, it's essentially trying to couple. Everywhere in the space is trying to couple at rate epsilon. And I haven't got the details on the slide, of course, but essentially what that means is you just run the process for a time t, which is exponential with rate epsilon, and that is enough time to guarantee a perfect sample, because that's the idea of coupling from the past, because everywhere in the space, you're coupling at rate epsilon. And I'm sure Christoph is about to raise another sign at me, so I guess I'll just say Here are a couple of references, and thank you again for a great paper.
Thank you. So this comment is together with Anthony Lee and Sumit Singh. And many of my points in the first slides have been mentioned already. And so I really would like to thank the authors again for inspiring work. And basically, I just want to say that I'm focusing on the kind of hard problem setting, the high dimensionality that has also been mentioned a few times before. So can we actually make this method to work with harder problems, high dimensional problems? And there were examples in the paper that show promise of the method for when you increase the dimension, like the Gibbs sampling case, as was described by John. And there were a couple of other examples discussed by Darren. And actually, what I would like to focus on is very much related to the AR example of Darren. So in a specific setting of time series models, specifically hidden Markov model smoothing, you can actually use this methodology by using couplings of so-called conditional particle filters, which were presented here 10 years ago. And there are a couple of ways to couple those methods, and there are a couple of variants of that method. But basically, they seem to actually work with long time series, which is equivalent to high dimension in this case for inference. And in particular, we were studying a coupled version of the backward sampling variant of this conditional particle filter, and that was actually suggested in a discussion note 10 years ago here. But that seemed to work really well in practice, but we were also able to prove something for that, to actually confirm that it does work quite nicely when you increase dimension. So what's the setting? The setting is that t is the time series length, but that is proportional to the dimension of the sample space here. And what we can show is that the tail probability of the meeting times satisfy, well, the assumption 2 is satisfied in the first place, but the constants there actually satisfy certain things with respect to the dimension or the time series length. And so actually the delta parameter is independent of capital T, yes, but the constant, that grows exponentially, which may sound bad, but it isn't actually, because we can also prove rather easily a upper bound for the bias correction. And you can see that if you increase k parameter linearly in dimension, then you can actually guarantee negligible contribution of the bias correction term. So it would be really nice to see other theoretical confirmations of the method working in high dimensions. That's all. Thanks.
Okay, thanks a lot for the interesting discussions. Maybe I'll just do it discussion by discussion. So it's interesting to see the example being implemented in different settings. So I was very interested to see the implementation in an AR1 setting and Gaussian random field setting, where obviously the difficulty there seems to be to do with the dimension, but also there's a parameter that has a very direct impact on the performance of the marginal algorithm, in fact. And so we see it in the meeting times. So like this alpha parameter, I believe. And it is the same in the time series setting, I guess. So you wouldn't see the same performance if you use a Gibbs sampler or a more specific method such as a conditional particle filter for the same type of models. It's interesting to see that indeed if you use random walk metropolis hastings for the full conditional updates, it's not clear that reflection couplings would help at all compared to independent maximal couplings. It's also, in any case, not clear what the best or optimal strategies would be at all, right, in this setting. It is true that in any case, if we imagine a parallel computing environment, every single processor will have to go through the burn-in of the marginal algorithm one way or another. I mean, even a perfect sampler, you would see that coming into the computing costs of the algorithm, presumably. That in some way might be a bit hard to escape. There's a problem of finding a place that we're not starting from in a high-dimensional space by doing a succession of local steps. So in any case, there's a certain number of steps that have to be taken. So yeah, that has to do with the marginal performance of the algorithm. So what's interesting is to find scenarios where the marginal performance of the MCMC algorithm is good, and yet the couplings are long for some reason. And those are the cases where there might be hope for better methods in the future. It was interesting to hear the discussion of Chris on the choice of K and M, so I should really point out that we are not always saying that you should use the 99th percentile of the meeting time as a choice of K. This is very much a heuristic, and again, let me reiterate that we hope that more work can be done on the choice of K and M. I would also like to say that if we were to rewrite the paper now, we would introduce a third parameter, which would be the lag, L. It has dramatic effect on the second moment of the bias correction term. And so in the same setting, if you choose very roughly, and again, there's no theory to back this up, but if you choose the lag to be in fact of the same order as K, so also possibly some large quantile of the meeting time, you will probably find that you'll decrease the variance a lot for a very modest increase of cost. Right? So of course, then there would be 3 parameters to choose. So this was really inspired by this follow-up paper with Paul Vanetti and Niloy Biswas on obtaining upper bounds on the total variation between the chain and the limiting distribution. We haven't tried all the couplings, and in particular, we haven't tried projection coupling. So thanks for raising that up. It'd be interesting to see if this can be used. And also, it's interesting that you've set M and then chose K, various K. So that corresponds to a practical setting where we have maybe a fixed constraint that would be more easily translated into a choice of M. Whereas in the paper, we tend to think of the choice of K and then M to be always a multiple of K, because intuitively we were thinking that we're going to throw away K over M iterations in sort of percentage, and so we want that to be small, and so we think of M as a multiple of K, but in other settings it could be more practical to set M and then fix K later. Thanks, Shaoli, for the. So when people think of the US academic system as competitive, so you see that your colleagues come across the Atlantic to outperform your work. But no, your proposal is very interesting, and also to do with the variance of this bias correction term, because it's true that I think it matches our experience as well, that this bias correction term, when it's not 0, it tends to take large values that really have an impact on the performance of the algorithm, and so any sort of methodological proposal to alleviate this issue would be, I'm sure, very useful to the potential users. Thanks to Andy Wong for suggesting and highlighting a link with regeneration methods and also to the interesting work that they've been doing. Indeed, I think of regeneration methods are really much like sort of the most compelling other thing that you can do in order to parallel MCMC calculations. So it'd be nice to see further links between the methods. And I also would like to thank Matti for the call for maybe obtaining more theoretical results. We do not have any results in that paper and of most of the follow-up papers on how the meeting times behave with either the dimension or also other important features that define the difficulty of the sampling problem. And even in our work on coupling conditional particle filter, we just prove that the variance is finite, but we don't say at all how it behaves with the important parts of the problem. So it's very interesting to see that this can be done in certain settings, and we're looking forward to seeing more examples where this can be done. Maybe I'll stop here. Thank you.